You know, when we think about high-performance sports equipment, we usually picture things being bolted down or like strapped in incredibly tight.
Right, locked in completely.
Exactly. I mean, think about stepping into a ski boot, where you have to basically crank those metal buckles until your foot is entirely immobilized.
Yeah, or look at a custom-molded carbon fiber cycling shoe.
Right. We had this deeply ingrained assumption across almost every athletic discipline that if you want to transfer power from your body to the ground, there just cannot be a single millimeter of wiggle room.
Your foot needs to be locked in, practically mummified in synthetic material.
Literally mummified. But welcome to the deep dive, by the way.
Yeah.
Today, our mission is to investigate a remarkably simple but revolutionary concept in biomechanics.
And it really is revolutionary.
It is. We're looking at how the shape of the toe box in your athletic shoes directly dictates your physical performance. We're pulling from a fascinating new 2025 biomechanical study titled Effect of Toe Box Size on Basketball-Specific Movement Performance.
Which is a bit of a mouthful, but the findings are incredible.
Totally.
Yeah.
And I'm going to tell you right now, whether you're out there grinding on a tennis court or, getting obsessed with competitive pickleball, or even if you just hate getting that throbbing foot pain after a gym workout, this analysis is going to completely change how you look at the shoes in your closet.
It really makes you second-guess your entire wardrobe.
Right. Okay, let's unpack this. For half a century, athletes have been told to lace up tight. Why did shoe manufacturers go all in on this narrow, restrictive design in the first place?
Well, it all stems from a concept called foot-shoe coupling stiffness.
Okay, foot-shoe coupling stiffness. What does that actually mean?
To understand the logic, you kind of have to look at it through the eyes of, like, a 1970s materials engineer.
Okay, I'm picturing a guy with a pocket protector.
Exactly. So when a player pushes off a hardwood floor to sprint or jump, they are generating immense physical force, right? The goal of the shoe is to channel 100% of that force directly into the floor. So the engineering logic dictates that you need a shoe that fits like a rigid external shell.
So no sliding around.
None. Because if the shoe is wide and your foot slides laterally inside it even by a fraction of an inch, the force you generated doesn't go into the floor. It gets lost as internal friction against the insole.
Ah, I see. It's just wasted energy.
Exactly. The prevailing theory has always been that any movement inside the shoe is a leak in your athletic potential. Stiffness equals speed.
So the modern athletic shoe essentially becomes a straitjacket for your feet.
That is a very accurate way to put it.
I mean, sure, you eliminate the internal sliding, but you're literally binding up the most important mechanical levers in your lower body.
Yeah.
You're wrapping tape around the hinges.
And the physical toll of that straitjacket design is staggering when you actually look at the global data.
How bad are we talking?
Well, because the industry prioritized this rigid coupling, an estimated 19% of the entire global population now suffers from structural toe deformities.
Wait, 19% of the globe.
Yes. The most common being hallux valgus, which is just the clinical term for bunions. We're literally talking about the physical realignment of the bones in the foot simply to conform to the unnatural shape of modern shoes.
That is hundreds of millions of people dealing with chronic foot pain. And it's essentially self-inflicted by, the athletic and fashion aesthetics we've normalized.
And the numbers become even more alarming when you isolate sports that require explosive dynamic movements, like basketball, which this study specifically examined.
Right, because basketball is just nonstop jumping and cutting.
Exactly. There are roughly 450 million basketball enthusiasts worldwide, and those players are at a massive risk for hammer toes, bunions, and chronic callus lesions.
Because the environment inside a standard basketball shoe during a game is just brutal.
It really is. You have constant pressure, high-speed friction, and a foot that is desperately trying to naturally splay out to absorb impact. But it's trapped inside a narrow, triangular toe box that simply won't yield.
Right, because when you run, your foot isn't just a solid block of wood slapping against the asphalt.
No, not at all.
It's a complex suspension system. It expands, it flattens out under load, and the toes naturally spread wide to grip the ground.
Precisely.
But if the shoe is shaped like a torpedo, those toes are just getting crushed together with every single step.
And beyond the obvious pain factor, this tight shoe theory is actually failing at the one thing it was designed to do, which is improve performance.
Wait, really? It makes you perform worse?
Yes. Traditional sports logic dictates that the narrow toe box improves power transmission. Anatomically, however, A narrow toe box restricts the metatarsophalangeal joint.
Okay, let's translate that. It's the big toe joint, right?
Yes, the big toe joint. When your big toe is squeezed inward toward your middle toes, a state we call passive adduction, it puts the abductor hallucis muscle under severe stretch.
And that's the muscle running along the inside arch of the foot.
Correct. When that muscle is stretched tight like a rubber band over the bones, that tension physically compresses the surrounding arteries,
Oh, wow. So you're actually cutting off blood flow.
mechanically bottlenecking the blood supply to the entire forefoot. Yeah. The tissue becomes starved for optimal blood flow, and the joint itself is locked out of its natural range of motion, so the body actually becomes measurably less efficient at pushing off.
So the grand irony here is that we're aggressively binding our feet, cutting off our own circulation, and giving ourselves permanent bone deformities, all under the false assumption that it makes us jump higher or run faster.
It's a massive contradiction, and that perfectly sets the stage for what these researchers in 2025 decided to test.
Right. They wanted to know if giving the foot some actual breathing room would maintain performance while saving the joints. Let's talk about the setup.
The structure of their experiment was incredibly rigorous. They recruited 30 university-level basketball players.
Okay, so high-level athletes.
Exactly, 25 males and 5 females. And they had them execute highly standardized agility drills. They didn't rely on simple stopwatches either.
What do they use?
The testing facility utilized force platforms integrated directly into the floor to measure exact physical outputs, along with optical timing gates and full-body 3D motion capture cameras.
That is some serious tech.
Yeah.
And the drills they chose were a 5-meter straight sprint, a 180-degree lateral shuffle, and a 45-degree sidestep cut.
Yep, the foundational high-torque movements of almost any court sport.
I mean, anyone who plays court sports knows exactly what these movements feel like. Sprinting forward to close a gap, sliding side to side on defense, and that aggressive, violent plant and cut to change direction.
Exactly, and the researchers tested these 30 athletes in 6 different custom-manufactured versions of the exact same athletic shoe.
So the foam density, the rubber grip, the upper materials, all of that was identical.
Entirely identical. The lacing system, too. They isolated the variables down to 2 microscopic modifications regarding the geometry of the sole.
Let's break down those modifications because I want to make sure we picture this correctly. One was called the SCL rotation, and the other was the TADL extension. Walk us through what they actually did to the shoe here.
Sure. So the SCL rotation stands for sole center line rotation. The researchers basically rotated the center line of the entire shoe inward by 2 degrees.
Okay, to visualize this, imagine taking a standard shoe and just slightly curving the front half inward.
Exactly. The goal was to see if matching the shoe more closely to the natural banana-like inward sweeping arch of a human foot would improve power transfer.
Got it. A 2-degree curve is subtle but makes sense anatomically. And what about the TADL extension?
TADL stands for toe allowance dividing line. For this modification, they left the curve of the shoe alone and focused strictly on the inner side of the toe box.
The specific area where the side of your big toe presses against the fabric.
Yes, that exact spot. They simply extended the fabric outward to make that section wider. They tested 2 specific widths, a 1.5 millimeter widening and a 3 millimeter widening.
Okay, wait. I have to stop you there and play the skeptic for a second. 3 millimeters.
Yes, 3 millimeter.
Try to visualize that. That is roughly the width of 2 pennies stacked together. My gym socks are thicker than 3 millimeters.
It sounds microscopic, I know.
I just struggled to believe that giving an athlete's big toe an extra 2 pennies of space is going to do anything measurable on a force plate. Are we sure any changes in their speed weren't just a placebo effect? Like maybe they just knew they were wearing a custom shoe?
What's fascinating here is that the data completely defies our intuition about physical scale. And the double-blind fourth plate measurements eliminate the placebo argument entirely.
Because the cameras and sensors don't lie.
Exactly. Let's look at what the machines recorded. The 2-degree SCL rotation, curving the shoe inward, yielded almost nothing.
Really, nothing at all.
It slightly altered the peak forward force during a sprint, but the overall performance benefits were statistically negligible.
So redesigning the entire curve of the shoe was essentially a dead end.
Yes. The breakthrough came entirely from the TADL widening.
The 3 millimeters.
When these athletes laced up the shoes that provided just 3 extra millimeters of space specifically for their big toe, the performance spikes were massive. On the 5-meter sprint, their times dropped by 6.53%.
Wow, a 6.5% speed increase on a short sprint just from unpinching the big toe.
It's incredible.
I mean, in a real-world scenario, that is easily the difference between beating a defender to a loose ball or getting your shot blocked into the stands.
And the improvements actually compounded during complex agility movements. In the 45-degree sidestep cutting drills, their completion times fell by 7.69%.
That is a huge margin in competitive sports.
It is. But the truly staggering metric, the one that challenges decades of sports science, is their propulsion impulse.
Okay, break that down for us. Propulsion impulse.
It measures the actual physical kinetic energy the athlete was able to drive down into the floor to launch their center of mass forward. That propulsion impulse skyrocketed by 27.27%.
27% more physical propulsion.
Almost 30%, yes.
If you told me a new pre-workout supplement, or like a carbon fiber spring, gave someone a 27% increase in explosive power, I'd assume they were cheating.
Right. It sounds like an illegal performance enhancer.
And we are talking about doing absolutely nothing more than letting the big toe sit in its natural anatomical position. A 27% jump from 3 millimeters of width just defies common sense. Mechanically, what is happening inside that shoe down at the bone level to generate that much extra force?
Well, we have to separate the physics into forward movement and lateral movement. Let's start with sprinting forward.
Right.
Adding 3 millimeters of width to the side of the shoe mathematically increased the flat surface area of the toe box floor by about 365 square millimeters.
Which creates a crucial pocket of negative space, right?
Exactly. This space allows the hallux, the big toe, to splay out completely flat and straight. The big toe functions biomechanically as a lever arm.
Right, our built-in lever.
When you wear a traditional narrow shoe, that lever is shoved inward. It is out of alignment with the metatarsal bones of your midfoot.
Oh, I see where this is going.
When your calf muscles fire to push off, the kinetic energy doesn't travel in a clean, straight line. A significant portion of that force gets absorbed, dissipated, and just lost inside the cramped big toe joint.
Ah, okay. It's like trying to pry open a heavy door with a crowbar that has a massive bend right in the middle of it.
That is a perfect analogy.
You push on the handle, but the force gets lost at the bend. The crowbar just flexes instead of popping the door open. But if you give the toe room to straighten out, you unbend the crowbar.
Precisely. It acts as a perfectly aligned, rigid lever, transferring 100% of the power from your leg muscles straight through the bones and directly into the floor.
That makes so much sense. You are perfectly optimizing the skeletal lever system.
Yes. Now let's look at the lateral movements, the sudden sideways cuts and heavy shuffles. This entirely comes down to the physics of friction.
Okay, friction.
The core formula here is F equals mana times N.
All right, let's translate the physics textbook for the layperson here. So F represents the maximum static friction force, which is basically your literal grip on the floor before the shoe breaks traction and slides, right?
Correct.
And F is the coefficient of friction, meaning how inherently sticky the rubber compound on the sole is.
Exactly.
And N is the normal force, which is essentially your body weight pressing down into the court.
You nailed it. So by widening the inner toe box by those 3 millimeters, the shoe manufacturer is physically putting a wider patch of rubber in direct contact with the floor.
Right at the exact pivot point where the foot rolls over during a cut.
Yes, you are radically increasing the functional surface area on the medial side of the forefoot.
It's the exact same logic as putting wider tires on a Formula One race car.
Exactly the same.
A wider contact patch touching the asphalt means a massive upgrade in grip for sudden stops, aggressive cornering, and rapid direction changes.
So when you combine them, you have a straightened bone lever for explosive forward momentum and a wider rubber contact patch for aggressive lateral stability.
I understand the mechanics of why they're moving faster, but that actually raises a serious concern for me.
What's that?
Well, if I have significantly more grip and I'm using this perfectly aligned bone lever to make faster, much harder directional cuts, doesn't that mean my knees, ankles, and hips are absorbing a much more violent impact?
Yes, the injury question.
Yeah, because if I'm cutting nearly 8% faster, that extra kinetic energy has to go somewhere when I slam on the brakes.
And that is always the primary concern among biomechanists when athletes get superior traction. You worry that the shoe grips the floor perfectly, but the knee ligaments absorb the rotational torque and just snap.
Exactly.
However, this study found something entirely counterintuitive regarding impact stress. They closely monitored the ground reaction force, or GRF, during the most violent deceleration phase of that sidestep cut.
And what did they find?
The peak GRF didn't spike, it actually decreased.
Wait. They were moving faster, planting their feet harder, stopping quicker, but the physical impact force radiating up into their joints went down.
It went down.
How is that mechanically possible?
Think about how a massive oak tree survives a hurricane. It doesn't rely on a single, narrow trunk bolted to the dirt. It relies on a wide, splayed network of roots spreading out in all directions to safely absorb and dissipate the wind's energy.
Oh, wow. That's a great visual.
When your toes are crushed together in a narrow toe box, your foot acts like a single unstable peg slamming into the floor.
Hmm.
The shock wave travels straight up your shin to your knee.
Because there's no base to absorb it.
Right. But when the big toe is allowed to spread out and act as an anchor point, it engages the entire network of stabilizing muscles in the arch and the lower leg.
The splayed foot acts as a dynamic suspension system.
Exactly. It actively controls the deceleration and smoothly dissipates the force, rather than just taking a rigid hammer blow to the joints.
So you were getting higher athletic performance and lower structural injury risk simultaneously, simply by allowing the foot to operate the way millions of years of evolution designed it to.
It's a win-win scenario.
Now, the study specifically tested university basketball players doing basketball drills. But the physics of a violent 45-degree sidestep cut are hardly exclusive to the basketball court.
No, not at all. The authors of the study make a point to explicitly state that these findings are highly applicable to any sport requiring high-frequency foot movements, rapid direction changes, and explosive short sprints.
Right.
They highlight tennis, volleyball, and football as direct beneficiaries.
We really need to emphasize tennis and pickleball here. I mean, if you've ever watched a professional tennis player returning a 120-mile-an-hour serve or a pickleball player engaged in a rapid-fire volley up at the kitchen line, their movements aren't just forward running.
It's extremely lateral.
It is non-stop lateral shuffling, split steps, and aggressive 45-degree lunges. You're constantly exploding side to side, putting all your body weight onto the inside medial edge of your shoe to break and push back to the center of the court.
The biomechanical demands are virtually identical to the basketball drills they tested. Whether you are playing on polished hardwood, a gritty acrylic hard court, or slippery grass, the requirement for a toe box that allows the big toe to act as an anchor is universal.
It really is.
The friction principles of the rubber and the lever mechanics of the bone do not change just because the ball is smaller or the net is lower.
It really makes you wonder how many thousands of tennis and pickleball players are out there suffering through foot cramps, plantar fasciitis, and sluggish reaction times simply because their trendy, brightly colored court shoes are forcefully squeezing their toes into a sharp point.
Probably a lot of them.
But as illuminating as this data is, we always need to examine the whole picture. What are the constraints of this research? Let's talk about the participant pool. 30 athletes is a solid sample size for force plate testing. But it was heavily skewed male, wasn't it?
Yes, it was 83.3% male, 25 men and only 5 women. This is a significant limitation that the researchers openly acknowledge.
Because men's and women's lower body biomechanics can differ substantially.
Very much so.
Right, like because of the Q angle, the anatomical angle from the width of the hips down to the knee, which affects how force is distributed through the foot. Not to mention general differences in ligament laxity and natural foot structure.
Exactly. Getting a perfectly stratified sample in elite university athletic programs is notoriously difficult, but future research absolutely must replicate this testing with a balanced gender pool. We need to ensure these specific 3-millimeter benefits scale identically across different skeletal structures.
That's a really good point. Any other limitations?
The other major limitation involves the internal measurements. They meticulously measured the forces interacting with the ground, but they couldn't directly measure the pressure distribution happening inside the shoe itself during these intense cuts.
Wait, why not? We have pressure mapping insoles now, don't we?
We do, but the current generation of in-shoe pressure sensors are still too thick and clunky.
Oh, I see.
If you slide a sensor board into a highly customized, precision-fit athletic shoe, you fundamentally alter the internal volume.
So the shoe just fits differently.
Right. The athlete subconsciously changes how they run and cut because the shoe feels different, which taints the biomechanical data. You cannot measure the natural movement if the measuring device itself ruins the natural movement.
That makes perfect sense. So where does the research go from here?
The authors note that the future lies in utilizing ultra-thin, flexible, wearable nanomaterial sensors that won't disrupt the fit.
Oh, that sounds very sci-fi.
Yeah, they plan to combine those with advanced dynamic 3D foot scanning to map exactly how individual foot shapes interact with different toe box volumes in real time under heavy athletic loads.
It really makes you rethink the entire paradigm of sports gear. We've spent a century building stiff, rigid shells and demanding that the human body conform to the equipment.
If we connect this to the bigger picture, this study represents a massive paradigm shift in the philosophy of sports science.
It really does.
We are finally transitioning away from the archaic practice of binding and restricting the foot. We are entering an era of designing equipment that unleashes the body's natural mechanics. The data definitively proves that when you respect human anatomy, athletic performance doesn't drop, it explodes.
So what does this all mean for you, the listener? Let's distill this deep dive down to the practical takeaway.
Yes, let's break it down.
The era of suffering through tight, painfully pinched athletic shoes in the name of locked-in performance is officially over. We now have the rigorous biomechanical proof that giving your big toe just 3 extra millimeters of space, a sliver of room no thicker than 2 pennies, not only saves you from the structural misery of bunions and compressed arteries, but it makes you measurably faster,
Dramatically more explosive, too.
dramatically, and far more stable on the court.
It fundamentally changes the criteria you should use the next time you visit a sporting goods store.
Absolutely. The next time you're shopping for athletic shoes, whether you're gearing up for a grueling tennis match, a weekend pickleball tournament, a pickup basketball game, or just hitting the gym for squats, don't just get hypnotized by the brand logo or the thickness of the foam cushioning.
Pay attention to the shape.
Pay close, critical attention to the toe box. Put the shoe on, stand up, and press your weight down. Can your toes actually splay out naturally?
That's the real test.
Can your big toe lie completely flat and straight without pressing hard into the side fabric? Because if it feels like a straitjacket for your toes, you aren't just risking a joint injury, you're literally leaving your own athletic potential trapped inside that shoe.
It is a powerful realization about how much trust we put into traditional designs. And it leaves us with a final thought to ponder as we wrap up this analysis.
Go for it.
If simply allowing a single toe to sit in its natural, uncompressed anatomical position can safely unlock a 27% increase in physical power, what other deeply traditional, tightly bound pieces of sports gear are you currently wearing that are actually suppressing your true athletic potential?
Man, a fascinating question to leave on. Thanks for joining us on this deep dive.